Mohammed Saifullah.
Yes, sir.
Okay. So we have to start with a new chapter, that is thermal properties of matter today. The other two chapters I will take your extra class to define. Okay, Saifullah.
Yes, sir.
So let's start with thermal property of matter. And this, we first start with what do you mean by temperature? Mamuna, any idea?
Temperature is a quantity which measures if the liquid or anything is at uh, high degree Celsius or low degree Celsius.
Okay. Saifullah, any idea?
Wait, one more for
No.
me.
Okay. Suppose we touch a particular object. Let's say this is a pen. If you touch it in summer, you feel nothing. But if you touch it in winter, you feel cold on touching it. It means if we touch a particular object, we define the temperature of that particular object with respect to ourselves. Or you can say we can define the hotness or coldness of that body with respect to our body temperature. So temperature is basically a relative term which is defined with respect to some fixed quantity. So temperature is simply the measure of degree of hotness or coldness of a body with some specified relative term is called temperature. So to measure this particular temperature, we may assign some unit. SI unit of this temperature is Kelvin. We may define some instrument to measure this temperature, which is called thermometer. And it will be based on two different terms. First is clinical, and second is laboratory. So clinical temperature or clinical thermometer range related to body temperature or human body temperature. So its range will be from 36 degree to 42 degree only. Or you can say it will be defined to measure human body temperature only. But laboratory thermometer is based on melting point of ice and boiling point of water. So it is based on so we can simply assign particular thermometer related to these two main scale. First is lower value melting point of ice and upper value or range of this particular thermometer to be boiling point. So on the basis of these two basic parameter, we can relate the temperature of a particular quantity about its hotness or its coldness. Is it clear?
Yes, sir.
Saifullah, any doubt?
No.
Okay, just write it down to this part.
Done, sir.
Yes, done.
Okay. Now to measure this temperature, let me define you how to use formula. So for any scale, we define a term T minus LFP divided by UFP minus LFP. In this, T is temperature on the scale. LFP is lower fixed point. UFP is upper fixed point. Lower fixed point is also called ice point, or you can say melting point of ice. You must have learned about melting point of ice in your earlier classes. It will be 0 degrees Celsius. Similarly, upper fixed point is also called steam point or boiling point of water. Saifullah, any doubt?
Is this the equation or formula?
Yeah, it is just a general relation to define any scale. I'm defining you how to use this formula. Suppose P minus LFP divided by UFP minus LFP equals to, if you are using Kelvin scale, so in terms of Kelvin, we write K. Lower fixed point is melting point of ice in Kelvin. It will be 273 divided by upper fixed point. It will be 373 minus 273. Similarly, in terms of Fahrenheit, it will be F minus 32 divided by 212 minus 32. In terms of Celsius, it will be 0 divided by 100 minus 0. In terms of resistance of platinum wire, we can use RT minus R0 divided by R100 minus R0 and so on. In any scale, you can use it. So this entire geometry of this formula will remain same. So you have to use the temperature, which we have to calculate. So you need just two terms. First is ice point related to that scale and steam point related to that scale. Then you can formulate your own formula related to this term. Saifullah, is it clear?
Yes.
Mamuna, any doubt?
No, sir.
Okay. Then related to this term, there will be a question. First, find temperature for which numerical value on two different scale will be equal to each other. Suppose there will be a question to find numerical value so that Kelvin and Fahrenheit are equal to each other. So just put K and F, X and X. and then simplify this expression, you will get K equals to F equals to 574.25. It means at this much amount of temperature, the numerical value of Kelvin and Fahrenheit equals to each other. Similarly, you must have learned about numerical equivalence of Celsius and Fahrenheit. It will be at minus 40 degree. Numerical part of Celsius and Fahrenheit will be equivalent to each other. Is it clear?
Yes, sir.
Okay, just write it down to this part. Abdul Wahid, just wait for 1 minute.
Done, sir.
Sir, can you explain what is K equals to F equals to 547.25?
Since if you have to calculate the temperature at which numerical value of Kelvin scale and Fahrenheit scale are equal to each other. So I just calculated that numerical part at which Kelvin scale and Fahrenheit are equivalent to each other. So just put K equals to X and F equals to X and equate these two expressions. On solving, you will get this much amount of temperature. It means at this temperature, Kelvin scale and Fahrenheit scale are equivalent to each other. Is it clear?
Yes.
Similarly, I have calculated for Celsius part. So these two questions will be asked in just 1 mark question.
Okay, sir, done.
Okay. Abdul Wahid, we have just started the new chapter, that is thermal properties of matter, in which I had defined about first temperature and then how to calculate temperature, that is called thermometer. So you may take a screenshot from this part. Wahid, done? Next is this part. Wahid, taken? Okay. Now, if you have to convert numerical value from one scale to another, so just put values in this part and try to equate to find them. Suppose find 60 degrees Celsius in Fahrenheit scale. So just put the value of C as 60 degree and equate these two equations to find F. Try to solve. Ramuna, just check your calculation. According to the relation, we have f minus 32 divided by 232 equals to c minus 0 divided by 100 minus 0. Put the value of c to be 60 and simplify it to find f. Saifullah, just check your calculation. Good, Maimuna. Minus 32 divide by 212 minus 32, it will be 180. C is 60 divided by 100. So this 0 and this 0 will cancel out. Move this 180 to right hand side. So it will be f minus 32 equals to 180 into 6 divided by 10. So this 6 and this 6 will cancel out. 18 into 6, it will be 108. So f will be minus 32 move to right side. So it will be 140. Good, Saifullah. Wahid, is it clear? Okay. So this is all about how to calculate temperature or how to convert one scale into another. Next, or the most important part of this chapter, start with expansion. Thermal expansion. Suppose if you have a solid, so there will be particle fixed at their own position at this point. in fixed order like this. So this particular arrangement will be at some lower temperature. Let's say at temperature T0. If you increase the temperature of this particular body, this arrangement may get differ, since on increasing temperature, thermal energy of particle will increase. So the separation between particles arrangement will also increase. So they may get separated like this, like this. So initially it was about this much length, but now on increasing temperature, it will become this. Initially, width of this particular rod was this length, and now it has this much amount of width. So you can say on increasing temperature, thermal kinetic energy of particle increases. So separation between the particle increases, hence solid get expand or substance get expand. So on increasing temperature, bond gets weakened. Thermal energy of particle increases, hence separation between them increases, so body get expand. Namuna, is it clear?
Yes, sir.
Saifullah, any doubt?
No.
Okay. So we have to define expansion in a particular solid in 3 different order depending upon length, area, and volume. So first define linear expansion of solid. In this expansion, we just consider width of that body very small as comparable to length, so we can neglect it. So suppose we have solid having length L0 at some initial temperature T0. So on increasing temperature, length of this particular object may get changed. So let's say length becomes L at some temperature T. This was initial and this is final. So change in length from this point to this point will be delta L. So we can define a term to define this expansion in length or contraction in length depending upon changing temperature, that is alpha, which is called temperature coefficient of linear expansion. This particular alpha is equals to change in length, that is delta L, divided by original length L0, divided by change in temperature delta T. So we can write this delta L by L0 as fractional change in length, divided by this delta T as change in temperature. So alpha will be equals to ratio of fractional change in length to the change in temperature. Length and length having same unit, temperature having unit Kelvin or Celsius. So SI unit is Kelvin inverse or Celsius inverse. First, write it down to this part, then I'm explaining you about alpha.
Turns.
Safila, you have written? Wahid, you have done? So this alpha, that is temperature coefficient of linear expansion, simply defines you at what rate length of this particular solid will increase or decrease related to change in temperature. So it is equals to delta L by L naught divided by delta T. So we can define it as the ratio of fractional change in length to the change in temperature. Now, if you expand this relation, this particular part, we have alpha equals to delta L by L naught times delta I. So just take cross multiplication. So delta L will be equals to alpha times L naught into delta T. delta L equals to L minus L naught, alpha L naught into delta T. Now move this L naught to right side. It will be L equals to L naught, alpha L naught times delta T. Take L naught to be common from these two terms. So you'll get L naught 1 plus alpha delta T equals to L. The expression of calculating length related to this alpha and change in temperature. So Fulna, is it clear?
What is alpha here?
I just defined this part. Alpha is temperature coefficient of linear expansion, which simply defines at what rate and with which rate length of particular solid will change with change in temperature. So alpha is basically the ratio of fractional change in length to the change in temperature. Is it clear?
Okay.
Just 1 minute. You can also say it defines the rate of change in length with change in temperature. Just write it down to this part.
Then, sir.
Saifullah, you have written?
1 minute, sir. Yes, finished.
Good. Wahid, done? Okay. Let me define your question related to this. If length of a rod at 27 degrees Celsius is 100 centimeter. Find temperature at which its length will become if alpha is 2 into 10 to the power minus 4 Kelvin inverse just use the above formula and try to find. In this part, we have initial temperature T naught as 27 degrees Celsius. This length 100 centimeter, write it as L naught, convert it into meters, so it will be just 1 meter. Final length is 101 centimeters, so it will be 1.01 meter. Alpha is 2 into 10 to the power minus 4 Kelvin inverse, or it will be equivalent to Celsius inverse also. So just put all the values in the above formula and simplify it. Sarfullah, any doubt?
No, I'm doing so.
Okay. Vaz, just check your calculation. Vimana, I think it should be in positive. Just check your calculation. Okay. Go ahead. You got any answer? Let me define you how to simplify it more simple way. You can write alpha equals to delta L over L naught times delta T. Move this delta T to left side and alpha to right side. So you may write it as delta T equals to delta L divided by L naught times alpha. Now put all the values. Delta T is temperature difference. So it will be T minus T naught, which is 27. Delta L is L minus L naught. So it will be 0.01 divided by L naught, which is 1. Alpha is 2 into 10 to the power minus 4. We can write by removing this decimal as 10 to the power minus 2. So T minus 27 equals to 1 upon 2. So it will be 0.5. This 10 to the power minus 2 on moving to numerator. Yes.
L is 1.01.
We have to calculate delta L. So which will be equals to L minus L naught. L is 1.01 minus 1. So it will be just 0.01. Okay.
Okay, okay.
So if you move this denominator to numerator, it will become 10 to the power plus 4, and we have already 10 to the power minus 2. So it will be 10 to the power plus 2, or it will be 50. Move this 27 to right side. You will get T equals to 77 degrees Celsius. Is it clear?
Yes, sir.
Saifullah, any doubt?
No.
Done, sir.
You all have written?
Yes, sir.
1 minute.
ahead.
1 minute, sir.
Saifullah, done?
Yes, sir, done.
Okay. Now there will be some application of this linear expansion. First, since alpha equals to delta L divided by L naught times delta T. So we can write delta L divided by L equals to alpha times delta T. So this delta L by L naught is nothing but change in length divided by initial length. So it is the ratio of deformed shape by original shape, which is also called strain. And in this term, this particular deformation is due to change in temperature. So we can write it as thermal strain. So you'll be asked to calculate thermal strain produced in this particular rod. So just multiply alpha by change in temperature. Next, thermal stress equals to Young's modulus times strain. We have strain as alpha delta T. So put it, so it will become Y times alpha delta T. And then force due to this change in temperature will be equals to Young's modulus into alpha into area times delta T. As Young's modulus equals to stress divided by strain. So we can write stress equals to Y times strain. Next, stress equals to force divided by area. So force will be area times stress. So we have just calculated these terms. So you will be asked directly to find these terms. So you may use these formula to calculate. Is it clear?
Yes.
Yes, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Saifullah, you have written?
Yes, done.
Okay. The next term related to this is about bimetallic strip. Suppose you have two different rods attached to one another. One of the rod is this. Next, attached to it, both are identical to each other and joined to one another. Let's say alpha of this is alpha 1 and alpha of this is alpha 2. Alpha 1 is greater than alpha 2. So you'll be asked, if you raise the temperature of this particular system, how will the shape of this bimetallic strip will change? Whether it will remain straight or it may curve. My question is, we have two different rods having different coefficient of linear expansion attached to each other. Now, if you raise the temperature of this particular system, so what will happen? Whether these two elongate with same rate, or you can say the two would be remain straight line or straight, or it may get curved.
Sir, it will get curved.
Okay, so next question would be towards which direction it will get curved. Suppose temperature is increased and suppose temperature is decreased. Safulla, any idea?
I think it will cover opposite ways.
Okay, in first part, temperature. So which one will be in convex side or concave side? Let me define you the concept. Suppose you have alpha 1 is greater than alpha 2. It means greater linear coefficient expansion will increase greater in length on increasing temperature. So a red rod will expand more as compared to blue rod. So it may acquire this shape on increasing temperature. Like this. Is it clear?
Yes.
You will say on increasing temperature, change in length will be greater in red rod as compared to the blue rod, since red having greater coefficient of linear expansion. So you'll be asked towards convex side, which rod will go? So you'll say the red one will be towards convex side and towards concave side, blue one. So again, the next question will be, if you decrease the temperature, so what will happen? Or which will go towards concave or towards convex? Saifullah, any idea?
I think it will go vice versa. Red will be concave, whereas blue will be convex.
Okay, red will be concave and blue will be convex. Okay. Mamuna?
I don't know, sir.
Okay. You will say, since alpha 1 is greater than alpha 2, so on increasing temperature, L1 will be greater as compared to L2. Similarly, on decreasing temperature, since alpha 1 is more as compared to alpha 2, so on raising temperatures, length will increase more in L1 as compared to L2. Similarly, on decreasing temperature, length will decrease more in terms of alpha 1. So L1 will be lesser as compared to L2. So red will go towards concave side and blue will go towards convex side. Amuna, is it clear?
Yes, sir.
Is it clear? Or do you have any doubt?
Yes,
No
sir.
doubt.
These two are of different metals or of the same metal?
Different materials so that they have different coefficient of linear expansion.
Okay.
So you will be given bimetallic strip having alpha 1 is greater than alpha 2. So you'll be asked, if you increase the temperature, so which will go towards convex side or concave side? So just remember this concept to define it. Just write it down.
Done, sir.
Saifullah, you have written?
Yes.
Okay. So this is all about how to calculate linear expansion and related problem to this linear expansion. Next is aerial or superficial expansion. Suppose you have a rectangular segment having initial length L0, initial breadth B0, like this. So this particular dimension of body is at some lower temperature, let's say T0. If you increase the temperature of this particular body, so there will be deformation in its shape towards all direction. So the length of this rectangular segment will become L. Similarly, breadth will be B. This expansion, you define first beta, which is called temperature coefficient of aerial or superficial expansion. So we can define it in terms of area as beta equals to change in area divided by initial area change in temperature. Again, delta A and A having same unit, so they will cancel out. So we're left with just delta T. So SI unit is Kelvin inverse or Celsius inverse. We can define this particular coefficient of areal expansion as fractional change in area to the change in temperature. So it will be the ratio of fractional change in area to the change in temperature. Is it clear till this part?
Yes.
Safullah, any doubt?
How do we pronounce P?
Beta.
Okay, that's
It's
beta.
Greek alphabet. Okay. Just write it down till this part. Safullah, done?
Finished, sir.
Done, sir.
Amina, done?
Yes, sir.
Okay. So next, if you rearrange this particular equation, beta equals to delta A divided by A naught times delta T. So delta A will be equals to beta times A naught times delta T. We can write delta A as A minus A naught beta A naught delta T. Move this A naught to right side. So it will be A equals to A naught plus beta A naught delta T. A naught and A naught common. So you're left with 1 plus beta delta T equals to A. So this will be your final expression to calculate area of this particular sheet at any temperature T. So simply beta defines you at what rate area is expanding on changing temperature of this particular system. Now, there will be a question related to this aerial expansion or superficial expansion. Suppose you have a rectangular sheet like this, and if a hole is cut out at this point, so you'll be asked, how will size of hole and cutout portion will change on increasing temperature? Saifullah, any doubt in this question?
Can you explain the question again?
Okay, we have a rectangular sheet from which a hole is cut out and placed at this point. So you have to define how will this hole and this cutout portion will change its area on increasing temperature, whether hole will shrink or this cutout portion will expand, or both will increase with same rate, or both will decrease with same rate. Saifullah, any guess?
I guess the size of the hole will decrease, whereas the cutout portion will increase.
Okay. Mamuna, are you
Yes.
agree with this part?
Yes.
Okay. Now just consider if this hole of this cutout portion is placed at its own position. It means this entire sheet will be as it is, and there is no cutout portion. Now, if you increase the temperature, let's say, take mark on it like this. So how will this mark position will change on increasing temperature? Whether it will increase or decrease? You will say it will increase linearly as proportion with the rest of the term. Similarly, this whole part will also expand similarly as its cutout portion. Let me define you why so. Suppose this cutout portion may have particle at its midpoint like this, from which this hole is cut out. So on increasing temperature, there will be no enough space to go further decreasing like this, since all particles are closely packed together. So there will be chance to separation or to increase the separation between them. So may get separated from each other to inquire like this. Is it clear?
Yes, sir.
Yes, sir.
Yes.
You will say, since all particles are closely arranged at this particular point as being solid, so there will be no enough space in between these particles to get shrink further on increasing temperature. So on increasing temperature, separation of the particle will increase. So it may acquire this configuration. So you will say both hole and its cutout portion will increase at same rate on increasing temperature. Both hole and cutout portion will increase with same rate on raising temperature. Okay, just write it down till this part. Done?
Done, sir.
Written?
Yes, sir.
Now the next question will be relate between alpha and beta. Relation between alpha and beta. As since this particular rectangular strip is composed of two different lengths, one is length and the other is breadth. So we can write length equals to L naught 1 plus alpha delta t. Similarly, length, so it will be B naught 1 plus alpha delta t. Now, if you have to calculate area, so area is nothing but product of length and breadth. So on multiplying these two terms, length into breadth equals to L naught into B naught 1 plus alpha delta t times 1 plus alpha delta t. So 1 plus alpha delta t to the power 1 and 1 plus alpha delta t to the power 1 will become 1 plus alpha delta t to the power 2. Now L into B will be A, L naught B naught will be A naught. Is it clear till this part?
Yes, sir.
Okay. Now, according to binomial expansion, as we have 1 plus x to the power n, on expanding, it will be 1 plus n times x. Using binomial expansion. It means the exponential will get multiplied with this coefficient of x. So we have 2, the exponent of this entire part, so it will get multiplied with this alpha. So you will get a naught 1 plus 2 times alpha delta t equals to a. So this is another expression what we got for this length into breadth. And initially, we have just defined beta to find a. So we can write a equals to a naught 1 plus beta delta t. Now in these two equations, we have dressed the all term same. So we can relate these two equations. So you get beta equals to 2 times of alpha. So we can say, or alpha equals to beta by 2. Saifullah, any doubt?
No.
Okay. Just write it down. Abdul Wahid, is it clear? Okay.
Done, sir.
Shafullah, you have written?
Yes.
Mamuna, done?
Yes, sir. Done.
Okay. Similarly, we may define volumetric part as well. Volumetric or cubical expansion. Suppose you have a cuboid having initial length L0, breadth B0, and height H0. On increasing temperature, so it may expand uniformly from its all dimension. So it will be L, B, and H. So related to this volumetric or cubical expansion, we may define another term that is called gamma, like we had defined for alpha for linear, beta for aerial. Similarly, gamma is for volumetric or cubical. So it is called temperature coefficient of volumetric expansion. So gamma is equals to change in volume divided by initial volume to the change in temperature. So we may define this particular gamma related to what we have defined for alpha and beta as fractional change in volume to the change in temperature. So it is the ratio of fractional change in volume to the change in temperature. Now, change in volume and volume having same unit, so they will cancel out each other. So you're left with delta T only. So SI unit of this will be Kelvin inverse or Celsius inverse. Now we may rearrange this particular term to find V as gamma equals to delta V divided by V naught times delta T. Just take cross multiplication. So delta V equals to gamma times V naught delta t. Now this delta v is nothing but v minus v naught gamma times v naught delta t. Move this v naught to right side. So you'll get v equals to v naught plus gamma v naught delta t. Take v naught as common. So you will left with 1 plus gamma delta t equals to v. So this will be your final expression for volume at any temperature T, which is similar to what we have got for length, area. Is it clear?
Yes, sir.
Okay, just write it down.
Done.
Done, sir.
Saifullah, you have written?
Yes, sir.
Okay. Now we have to define a relation between alpha, beta, and gamma. So let me define you the relation between alpha and gamma. As this cuboidal part having length, breadth, and height, so we can write length equals to L naught 1 plus alpha delta t. Similarly, breadth equals to B naught 1 plus alpha delta t, and height as H naught 1 plus alpha delta t, as these all are nothing but length in different direction. So length will increase with same rate as of alpha in all direction. That's why I have taken length, breadth, and height all are alpha dependent. Now, if you multiply these three equations on multiplying, you'll get length into breadth into height equals to L naught, B naught, H naught. And 1 plus alpha delta t, we have 3 times. So we can write 1 plus alpha delta t to the power 3. Now this entire part is nothing but volume. This will be V naught. And according to binomial expansion, we can move this 3 to the coefficient of this alpha. So it will be 1 plus 3 times of alpha delta t. So this will be your function for volume. Mamuna, is it clear?
Yes.
And is equals to V naught 1 plus gamma delta t. Now on equating these two equations, on comparing these two equations, we can say gamma will be 3 times of alpha, or alpha equals to gamma by 3. Is it clear?
Yes.
Saifullah, in and out?
No, sir.
Okay, just write it down.
Done.
Saifullah, you have written? Abdul Wahid, any doubt? Okay, now we have just defined alpha in terms of beta, alpha in terms of gamma. So on comparing these three all, we can say alpha having one dimensional, so just divide it by 1. Beta having 2 dimensions, so just divide by 2. And gamma is 3-dimensional, so just divide by 3. These all three will be equal to each other. So one of the relation between these two terms will be this. Next, take the LCM of this 3 term of this denominator, so it will be 6. Multiply with entire part. So it will be 6 alpha, 3 beta, and 2 gamma. So the relation between these 3 terms will be either this part or this part. Is it clear?
Yes.
Yes.
Okay. Now there will be questions related to this. If linear expansion coefficient is 0.2 into 10 to the power minus 3 Kelvin inverse, find fractional change in volume at 100 degrees Celsius. Try to find fractional change in volume means delta V by V naught. We have to calculate. We have alpha. So alpha is 0.2 into 10 to the power minus 3 Kelvin inverse or Celsius inverse. So for change in volume, we have to define gamma. So gamma equals to 3 times of alpha, according to the relation what we have derived. Put the value of alpha in this part, you'll get gamma. Then, since in this question we have to calculate fractional change in volume, so it will be nothing but delta V by V. So gamma was delta V by V naught times delta T. So delta V by V naught will be equals to gamma times delta T. Just put all the values in this part, you'll get fractional change in volume. You may write it as temperature changes 100 degrees Celsius. Saifullah, any doubt?
No.
Okay.
So, sir, here delta T is equals to 100 degrees Celsius, right?
Yeah. And change in temperature in terms of Celsius and Kelvin is same. So we can use Kelvin or Celsius, it will give you the same value. Amina, just check your calculation. You have done a little mistake. Fawaz, just check your calculation. 100 will be 10 to the power plus 2. Good, Saifullah. Good, Fawaz. Wahid, send your answer. Three times alpha. Alpha is 0.2 into 10 to the power minus 3. So it will become 0.6 into 10 to the power minus 3. Good, Mamuna. So it will be 0.6 into 10 to the power minus 3. And delta T is 100. So it will be 10 to the power 2. So you may write it as 0.06. And since this fractional change in volume, so it will be unitless quantity. So it will be as it is. So do you have any doubt to this part?